The absorb bioresorbable vascular scaffold system is a flexible polymeric cardiac stent that can elute drugs and degrade into the body after its clinical need has ended. Stents are implantable biomedical scaffolds which are generally cylindrical and function to hold open and sometimes expand a segment of a blood vessel or other anatomical lumen. Traditionally, stents have been made from metals, which are permanent, stiff, and have been identified to contribute to the process of restenosis and other potentially adverse effects, such as stent thrombosis. In many treatment applications, the presence of a stent in the body may be necessary only for a limited period of time until its intended function is accomplished. Therefore, stents fabricated from biodegradable, bioabsorbable, and/or bioerodible materials may be configured to meet this clinical requirement. Developed in 2011 by Abbott Vascular and receiving FDA approval in 2016, the Absorb GT1 stent is made out of one such biodegradable material, PLLA, or poly-L-lactide. This device can be used to deliver drugs and possesses mechanical properties that permit arteries to flex and pulse naturally, reducing the likelihood of future blockages that are associated with metal stents. We classify this product as a device involving a chemical reaction. Once in the body, the stent undergoes hydrolysis to lactic acid that is metabolized by the body. During this process, the mechanical properties of the stent asymptotically approach those of the lumen which it supports, allowing the blood vessel segment to heal properly, reducing risk of restenosis.
The structure of stents is typically composed of a scaffolding that includes a pattern or network of interconnecting structural elements, or struts, rolled into cylindrical shape. Key design mechanical traits for coronary stent candidate materials include high elastic moduli to impart radial stiffness, large break strains to impart the ability to withstand deformations from the crimped to expanded states, and low yield strains to reduce the amount of recoil and overinflation necessary to achieve a target deployment. In designing such a system, selection and manufacture of a polymer that both exhibits these mechanical properties and can degrade within a desired timeframe with limited inflammation and restenosis is of critical importance. The semicrystalline polymer, PLLA, is one such material and already finds widespread clinical use with applications in resorbable medical implants. The ordered polymer chains constitute the crystalline component of the semicrystalline polymer, and the random polymer chains form the amorphous segment. Because the amorphous regions are less packed and therefore more accessible to water, the amorphous polymer is more susceptible to hydration than the semicrystalline polymer. For objects like this stent, which have a smallest dimension of roughly 100 micrometers, hydrolysis byproducts cannot readily diffuse out of the object, and bulk degradation, more or less from the inside, controls this process. The rate of stent degradation depends on the concentration of ester bonds, water, and carboxylic acid end groups. The carboxylic acid end groups are generated by each hydrolysis reaction. From a chemical standpoint, resorbable implants undergo 5 stages of degradation. The first stage is hydration of the polymer. After implantation of the polymeric resorbable device, the polymer begins to absorb water from the surrounding tissue. In general, polylactides are relatively hydrophobic. The chain ends, however, are hydrophilic due to the carboxylic acid end group. Chain ends cannot participate in a crystalline lattice. Therefore, the hydrophilic chain ends are relegated to the amorphous phase, rendering it more hydrophilic than the bulk. The second phase is depolymerization by hydrolysis. This manifests by a reduction in molecular weight. The third stage is a loss of mass, which occurs when the implant no longer has cohesive strength and the polymer starts to fragment into segments of low-weight polymer. Subsequently, radial strength reduces as a result of the scission of amorphous tight chains linking the crystalline regions. Finally, polymer chains have been hydrolyzed to sufficiently short lengths so that they are increasingly hydrophilic and able to diffuse out of the device and be resorbed into the body. The fourth phase is assimilation or dissolution of the monomer. Phagocytes can assimilate small particles and lead to soluble monomeric anions. Lastly, the soluble monomer, L-lactate, is changed into pyruvate, which eventually enters the Krebs cycle and is further converted into carbon dioxide and water. These final products are excreted from the body through the kidneys or lungs, which results in complete bioresorption of the implant.
Polymers comprising substantial quantities of D-lactate or other comonomers exhibit shorter degradation times as a result of increased disordering of the chains. This disordering decreases the percent crystallinity of the stent and increases the amount of amorphous polymer which can participate in hydrolysis, resulting in more rapid degradation. As other mechanical parameters such as the elastic modulus, the break strain, and yield strain are dependent upon the percent crystallinity, but as design parameters are secondary to the time of degradation, these properties appear more serendipitous than deliberately designed. These inherent potential mechanical shortcomings, however, can be compensated for by control of stent strut dimensions, since increasing the thickness of the struts proportionally increases the strain levels that can be imposed on the material. Apart from mechanical properties, a significant shortcoming of biodegradable polymers is that they are radiolucent with no radiopacity. Biodegradable polymers tend to have X-ray absorption similar to body tissue. In a second-generation product, this may be overcome by application of radiopaque layer by including a radiopaque agent dispersed within a second bioabsorbable polymer. The lifetime of the radiopaque layer can be controlled through selection of the bioabsorbable polymer in the radiopaque layer, as was done by the main scaffold. The Absorb BVS is a flexible polymeric cardiac stent that can elute drugs and degrade into the body. This is a promising technology that is both effective and sustainable long-term.